One major source of applications for nonlinear systems is Newton's second law. So if we take a look at this, we can rewrite this as a second order equation, and we'll assume that we're in one dimension here just to simplify things. And we'll take this function to be some generally nonlinear function. Now we can obviously do some manipulation and rewrite this equation as this following general form. Now we're going to try to introduce two things here. Number one, there's going to be a nonlinear system that we can take out of this, but we'll hold off on that for a moment. But the second thing that we're going to talk about is a hidden property somewhere in here. And what I mean by that is, if we take this equation, let's multiply both sides of it by x prime. You might say, well, why would we want to do that? This just seems to complicate things. It might seem that way for now, but actually this turns out to give us something very useful. This term here, if you take a look at it, you can interpret this as the derivative of 1/2 of x prime squared. Because if you just follow the chain rule, you'll get a 1/2 to x prime times x double prime, which is just the term we've got in the equation there. And for this other term, if we let v of x be the antiderivative of this force function, that means v prime should just be the force function. And that means that if we wanted to take the time derivative of this v prime, we would get, or this v, we'd get a v prime times an x prime. And that would just give us an f of x times x prime. And so, what we're able to do is to take that Newton's equation, scale it by this function x prime, and when we do that, it will turn out that this entire side here is a perfect time derivative. It's a perfect time derivative of this expression here. And what we found is that this time derivative has to be equal to 0. So that means this quantity right here, we're going to call this quantity E, and this quantity E has to be a constant. Now, if you know a little bit of physics, you probably see what's going on immediately. This quantity right here is referring to some sort of kinetic energy. It's 1/2. There's an m in there, so you can think of this as a kinetic energy per unit mass. So you could think of this as a 1/2 v squared. And this term over here, this v prime of x equal to f of x, this is just some sort of potential energy per unit mass. And so what we've done is we've shown here that the total energy, kinetic plus potential, is conserved in time. And so sometimes we take these second order equations that we've got, and we say that an equation like this is called a conservative equation. And it's called a conservative equation because there is some quantity that is conserved. And the quantity here is the total energy. And it's conserved in time. And we'll talk about that in a different context a little bit later. Sometimes they like to call this total energy the Hamiltonian. But we won't really need to get into that. The point of the story is Newton's law gives us this conservation. Now we're going to hold on to this conservation idea because it's going to help us in our second interpretation here. Now what we would like to do is write this in the phase plane. And what we're going to do is convert this Newton's law to a second, or sorry, not a second order, to a nonlinear system. And we will do this the same way we always do. We're going to let y equal x prime, so that's going to be our velocity. And y prime will then be x double prime. And from the equation, this is going to be negative f of x. And what we'll have then is our nonlinear system. We'll have x prime equals y, and we'll have y prime equals some negative f of x. And again, the negative there is some unknown function. It's a mystery function. And so what we would want to do here is study this system. Now, there's a big note here. Remember that the energy that we came up with, we can now interpret that energy here. It's 1/2, it was x prime squared. So this is going to be 1/2 y prime squared plus some function v of x, and this has to be constant. This thing is going to give a relationship between our solution, x of t, and y in the phase plane. So this is going to give us trajectories in the phase plane. So right away, in one of these conservative systems, we immediately get that the energy produces trajectories in the xy, or the position velocity phase plane. So let's go ahead and study this system the way that we've been studying it. We'll talk first about the most important feature here, these equilibrium points. All the behavior seems to center around equilibrium points. Now, to find the equilibrium points, we need to have x prime equals 0, y prime equals 0, which is the same as saying y equals 0 and negative f of x equals 0. Well, y equals 0 means that x prime equals 0, means that x is a constant. Y equals 0 means that the velocity is 0. So sometimes they like to call equilibrium points fixed points because things are not moving. Your velocity is 0. Equilibrium points in the phase plane have to happen when y is 0 and x is some constant. And you also need that this force function has to be 0, or the derivative of the potential is 0. So in your phase plane, whenever you go ahead and you study this, we're going to do a lot more here, but all of our equilibrium points are going to have to live somewhere on this x-axis. They all occur at some c in 0. They are going to be related to critical points of this potential energy. Somehow that's going to kick in. But it's points where we've got this force function is 0. Okay, so the next thing that we want to do is talk about a linearization. Now, as always, we want to go ahead and we want to linearize about these critical points, or sorry, the equilibrium points. We want to linearize about these points c and 0, wherever they happen to be. Now, to do that, what we're going to need is the Jacobian. And the Jacobian requires us to interpret this system here that we've got. X prime is y. This thing is going to be what we call f. Y prime is negative capital F of x. This is what we're going to call g. And so the Jacobian at our points x and y is going to be these partial derivatives in here. And because we've got this conservative system, there's going to be some symmetry here that will always be the case. The x partial derivative is going to be 0 up there. We'll always get a 1. We'll always get a negative f prime of x here. And we'll always get a 0. So the Jacobian is there. Now, note we will be almost linear when the determinant of this matrix is non-zero. So that means we're going to be almost linear when this f prime of x is non-zero. Remember that f prime of x is just related to this potential energy here. So this Jacobian expression, remember we're going to have to plug this in at the equilibrium points. Remember, the equilibrium points are just constants. Now, the next thing we're going to want to talk about are the eigenvalues. So what we need is the determinant of the Jacobian at this equilibrium point, c in 0 minus lambda I equals 0. That's what we need to solve. We'll get negative lambda 1, negative f prime of c and 0, and negative lambda there, sorry. And that's got to be 0. So we'll get lambda squared plus f prime of c is 0. And that's going to tell us that lambda is plus or minus the square root of negative f prime of c. Or another way of writing it would be negative v double prime of c. And so here's another interesting feature of conservative systems. There's only two options possible. The only options work like this. When v double prime of c is negative, or another way of putting it, when f prime of c is negative, that means this lambda will be real, and we will get equal and opposite eigenvalues. So we will end up getting a saddle. So there is option 1. When we have this v prime double prime negative, we will end up with the saddle. The other option is when v double prime of c is positive, or f prime of c positive. And in that case, we will get these eigenvalues plus or minus I beta. What we're going to get is a center. Now up here, remember, we'd have lambda plus or minus some beta. And that's going to give us a linear center. Now remember, when you've got a linear saddle, it implies you always have a saddle. So you will get a nonlinear saddle. But when you have a linear center, you have to be really careful because it may not be a nonlinear center. But we are in a special situation. We're in a special situation here where we're talking about a conservative system. And because we're in a conservative system, we have the advantage of that conservation equation. So I'm going to put a big but right here. In a conservative system, we get additional information. Remember, in the conservative system here, this energy function, the total energy function was 1/2 y squared plus v of x. So the partial derivatives here are going to be v prime of x and y. So those will be the partial derivatives here. So the critical points for the energy happen when y is 0, so when the velocity is equal to 0, and when v prime of x is 0. So the point of all of this is that the critical points of the energy are exactly the same as the critical points of this potential energy. And now that means we can use the standard sort of classifications that we've got. At the saddle point, remember here that at the saddle point and at any equilibrium point, we've got v prime of x is 0 and we've got v double prime of x is a negative, or sorry, at the negative there. And at the center, we've got v prime of x has to be 0 and v double prime of x has to be positive. Now we are interested in talking about the center here. So what's going to happen here is that what we've got is we've got a minimum in this potential energy, which is the same as a minimum in the total energy function. Now, the total energy function is a function of two variables. And when we've got a total energy function of two variables and we've got a minimum there, that means any time we have level curves around it. Remember when we talk about these E of x equals some constant, these are level curves. And that means around the level curves, we are going to have closed orbits when we've got a minimum. And that's an argument that you can make to try to justify why the center of a linear conservative system will also imply that it's a center for the nonlinear system. And that's going to tell us all we need. When we've got a conservative system, there's only two things that can happen. We can have equilibrium points that will be either saddles, they'll be either centers. We've got a conservation equation that tells us exactly what the closed orbits are going to look like, or not the closed orbits, what any trajectories are going to look like in the phase plane. So we can sketch fairly easily what things are going to look like. Now here's an example of a system here. So this example here, we're going to rewrite in the following way. We'll get 1 minus x squared is 0. This thing right here will be our force function, 1 minus x squared. So v of x will be its antiderivative, will be x minus x cubed over 3. Now the conserved quantity is going to work like this. We are going to say, first of all, that y is equal to x prime. Y double prime is x double prime is going to be negative 1 plus x squared. The conserved quantity, this total energy, is going to be 1/2 y squared plus the potential function v of x. So it's 1/2 y squared plus x minus x cubed over 3. That's going to give us trajectories in the phase plane. So we're going to construct that. Here's our system. X prime equals y prime equals negative 1 plus x squared. We're going to find the equilibrium points. Now, as always, this means that y is equal to 0, the velocity is 0, and it's going to tell us that negative 1 plus x squared is 0. So x will have to be plus or minus 1. So the two equilibrium points that we've got here are negative 1 and 0, positive 1 and 0. We're going to want the Jacobian. So this thing here is defined to be f, that thing there is defined to be g. So the Jacobian for us is going to get a 0, a 1. We're going to get the x derivative as a 2x and a 0 here. Now, at either one of these equilibrium points, we will see that the matrix will be invertible, so it will be almost linear for both. We can invert both of these things. So what we're going to want to do is find the eigenvalues. You can go ahead and do this individually, and I might as well just do this since I'm here and I've got it written out. We'll get lambda squared plus 2 is 0, so lambda will be plus or minus root 2i. And over here, we'll get negative lambda 1, 2. Negative lambda is 0. Lambda squared minus 2 is 0. We'll get lambda is plus or minus root 2. So we'll get a saddle at the point 1, 0. And we'll get a center at the point negative 1, 0. Now, these will end up being nonlinear versions as well. So when we linearize, we zoom in, and when we zoom in, it looks like they're linearized counterparts, but it will turn out that for linear saddles will always be nonlinear saddles, and in the case of a conservative system, a linearized center will always be a nonlinear center as well. Now, I won't show it here, but there are eigenvectors that you can find. So for the eigenvalue of 2, you will find that your eigenvector will be 1 and root 2. And for your eigenvalue of negative root 2, you will be able to find that your eigenvector will be 1 and negative root 2. So all of this is going to be enough for us to be able to sketch a phase portrait. And the phase portrait is going to look something like this. We're going to take our x-axis and our y-axis. We're going to have 2 equilibrium points. Remember that they always have to be on the x-axis. For a conservative system, equilibrium points happen when we've got 0 velocity. At the point 1, we've got a saddle, and we've got our 2 eigenvectors pointing in different directions. So we'll have one eigenvector that points like this, and the other one that points in the negative direction, like that. And over here, we've got a center. Now, the level curves of this function, the energy function, which was 1/2 y squared, and we had a plus x minus x cubed over 3. If we set this to be different values, we can end up plotting this in Maple. You can use the implicit plot command. And what you'll find is that there'll be a variety of things that go on. So along these eigendirections, you'll get these constant solutions, kind of like this. Now, for the eigenvalue of root 2 will be in this positive direction. So as t goes to infinity, all the trajectories are going to approach this direction here. And from t negative infinity, everything will start off this eigendirection. So what we'll find is that over here, the saddle behavior will kick in. But it's on the other sides that interesting things will happen. And this will glue us together to the saddle. Now, along the center, we are going to have some closed orbits, kind of like this. Now, we're not really sure if they're circular or anything else. I'm going to take advantage of seeing this plot in Maple, and I'm going to sketch one particular curve here. There's one particular curve that when E is 2/3, we are going to get this curve that's in the blue line. And that curve is called the separatrix. What it's going to do is separate trajectories that live for one kind of behavior from another one. Now, inside this separatrix, what we're finding is that we're going to have these closed orbits. We can assign a direction to the closed orbits. So remember that our system here looked like this. X prime is y, and y prime was, I can't remember right now, is a -1 plus x squared. When y is 0, we're going to be on the x-axis, so we're going to be at some point over here. So let's say I go and I talk about the point x equals 0 as well. And at the point x equals 0, that means y prime will be -1. That means is negative, and that means that y will be decreasing. So at this point 0 right here, the trajectories have to be going down. And you can find that with a similar argument, all the trajectories are going to be circling this way. And the same thing is going to happen. This separatrix here is this special trajectory that if you are on that value E equals 2/3, you'll stay exactly along this closed orbit. But anything less, so for E less than 2/3, you'll be inside and you'll be in these closed orbits around the nonlinear center. But for anything outside, you will be greater and you'll be whisked away. So you'll have these long orbits that kind of do something like this. They'll come off the one eigenvector and then come back to the other eigenvector. And these conservative systems are kind of neat. They tell you pretty much a good story, even with a difficult to solve nonlinear system. We're fortunate that it has this structure that allows us to take a look. Now remember, note that v of x was x minus x cubed over 3. This ends up looking like a cubic function. And the minimum of this cubic function was at -1. The maximum was at +1. So in some way we can see that the center is a stable equilibrium point here. And you can imagine that if you put a little bead in the bottom of that potential, it's like being in the bottom of the well. It will just kind of change its position, oscillating back and forth. And that's why you see those closed orbits. But if you were at the top here, you would fall off. It would be unstable. So you could see that at the saddle, you don't stay on the saddle at all. You move off. Every conservative equation can be written as a system and treated like this. They'll all have saddles. They'll all have centers.